So for the purposes of the recording, what should I call you?
Tony. Tony's
Tony.
good.
All right. Awesome. So, funny enough, I actually did go over USub with another one of my students just the other day. So
Awesome.
let's actually. I'm actually gonna use like the very first example that we talked about earlier.
Okay.
Yeah. And of course, I should probably share my screen so that you can.
Yeah, I was gonna say, how am I gonna see this problem? You want me to like Google it or
Yeah,
yeah?
you should. Yeah. All right. Cool.
All right. We have full screen this. All right.
So if
Ready.
I gave you. Oh man. There we go. My tablet's working now. So if
All
I
right.
gave you, can you see what I'm writing over here?
Yeah, I can see it. You're good.
All right. So there's some really easy cases you should look out for. So in other words,
Mm-hmm.
if you have a function, right, with whatever is inside of that function being whatever is like its own derivative, then
Yeah.
you could have u be that inside function. So you could
Okay.
have u be g of x, and of course du is going to be g prime of x.
G
When you're
prime
converting
of
to
X. Okay.
yeah, when you're converting to the u world, you also want to take care of the du and the dx. So gx
Yeah, and then
times
you divide it by GX, right, or something like that. You divide
uh,
the left side, so it's du over GX.
well no, so you're trying to get rid of everything that's x, right? So
Mm-hmm.
over here, this is the gx dx, this is the gx and the dx. So that's going to be replaced by du, right?
Yeah.
And then, of course, over here we have just the regular u and the regular gx,
Okay.
right? Which is also over here. And so with this would convert to the integral of f. Notice we replace gx with u, so f of u
Yeah.
times du. And if
Times
this was
U.
like an easier equation, right, you would be better off this way.
Oh, okay.
So so we're not going to actually evaluate the integral. We'll just try to learn to do the conversion. So
Yeah.
we'll have x squared plus 1 times 2x times 2x dx. So in this case, what should our u be?
The x2 plus 1.
Yeah, x squared plus 1, and then the du is equal to
2x.
2x dx.
Dx, yeah, sorry.
Yeah. Remember, I actually had a lot of trouble with u substitution when I was first learning it, just because I would keep forgetting the dx, and I was like,
Mm.
what is allowed to be substituted, what isn't, right? And so with that, what do we know? What do we
It's,
get as our new integral?
the integral of u times du.
Yep, u du.
Yeah.
All right. So yeah, whenever you're trying to do u sub, you have to get rid of everything in terms of x and the
Okay.
derivative. And if you see that the derivative of the same function also exists, then you know you found your u and du.
Okay.
Yeah.
That works. I see. I used to like do on the du part. I used to do like divided by 2x, so you get du over
Du
d.
dx. Yeah.
Yeah, uh-huh. And then
Yeah.
I would substitute it in, cancel it out. But I didn't know you could just put it in. That makes it a lot easier.
Yeah.
Okay.
That's that. I think that makes it a bit more intuitive.
Okay.
All right. In fact, let's actually go over a case where division is actually going to be a bit necessary. So what
Okay.
I'm going to do, I'm going to use the square root of square root of x cubed. Let me zoom in a bit. Plus 4 times x squared dx. So
All right.
this one isn't too similar. So what do you think our u should be?
X3 plus 4. Or x to the cube plus 4.
Yep, x cubed plus 4, x to the third plus 4, and then our du.
Is 3x. Wait, yeah, 3x squared.
3x squared. But notice, this is only an x squared here.
Yeah.
So how can we turn this into just an x squared?
You multiply by 1/3.
Yep. Yeah. So 1/3 du is equal to x squared. All right. Cool. We have our d, and then of course dx. Look, even I'm forgetting it sometimes.
Yeah. So then it would be integral u times 1/3 du.
Yeah. So you could actually factor out the 1/3, and so it's just
Oh
once
yeah,
again,
Put it in
u
front.
du. You see?
Yeah.
Yeah.
The U stuff I got, it's more like the complex stuff, like the trig stuff, where it's like,
Yeah.
okay, like identifying all the stuff you need to know.
Okay. So first, let's do some substitution with trigs, and then
Okay.
we're gonna do trig substitution. So
Okay.
I like to differentiate them because one, you're just like pulling a trig function out of nowhere, while the other one, like the u and du, are clearly available on the screen.
Okay.
All right. So you know what? So actually, before we start, do you know what the du of sine is?
Negative cosine.
Sorry, yeah. It's actually just cosine. Remember, we're taking the derivative, not the integral.
Okay. Yeah.
Yeah. And of course, dx of cosine.
That's the negative one.
That's negative sine. Yeah.
Okay.
And then of course, if you just stick on a negative, the other negative shows up. Stick on a negative here, this becomes positive.
Yeah.
All right.
Let me write those down.
So, have you ever discussed Riemann sums?
It sounds a little familiar. Yeah.
So in other words, given, so like you have two different types. You have the left hand side and the right hand side, right? So like given a function, right, you have to like split up the interval into some amount of points.
Yeah. Like n equals 3 or something.
Yeah. So
Yeah,
like
okay.
that one, right, and then
another one. Yeah.
yeah. So you're essentially approximating it.
Mm-hmm.
And so like here you would call this like your delta x, and then you would just add all of these points, right? You know, x1, x2, x3, right?
Yeah.
Yeah, so you'd multiply dx by like each of these values, right? So
Yeah.
So it would be the sum. You remember seeing the symbol, right? You're not scared of this one?
Yeah, it's the sum of everything.
Yeah. So the sum from sum from 0 to n of xn times del x. Right? So in other words, you're just adding all these rectangles.
Okay.
All right. This and this should not look too different from like the integral formula, right?
Yeah.
From-
It's like the first thing we learned. We learned these before integrals, like doing it like by n, and then you like just multiply it. So if it was, you'd multiply like f of x by 1, then f of x by 2, then f of x by 3. If these were like x1, x2, x3. Yeah.
And so this is literally just the same thing, right? I had a student ask me why we have to put dx. It's because it's just a very good approximation of our delta x, where dx is essentially just delta x as it goes to 0, because we're trying to make this as small as we can.
Okay.
So that's why I have to use dx, and like why it's really important. All right. Anyways.
Do you mind if I use the bathroom real quick? I'm so sorry.
Oh yeah, no, of course. Take your time.
I'll be back. Yeah.
Yeah. All right. Yeah, we're back. So I was gonna go over yeah, we're gonna go over a specific example.
That's good.
So okay, this one is actually okay. Integral of tangent x.
Okay.
All right, this is a big one. Notice there's nothing to really sub for u, right? Like
Yeah.
there's no like derivative of tangent that exists somewhere here.
Mm-hmm.
So, are we stuck here?
What was that?
Are we stuck here, or do you have a way to resolve this?
Um, you would have to find the antiderivative, which is like SEC squared, right?
Uh, the der- well, actually, so the antiderivative of tangent is actually a bit more complicated, which is why like we
Oh,
have to use the use up here. Do you know any
uh,
properties of tangent? Tangent is equal to.
it's equal to like 1 over something, I
You
think,
could
or
say
like
you could
one.
say it's 1 over cotangent,
Oh
but
yeah,
that doesn't really help. There's another really famous one. I wanted to see if you know.
yeah. No, I
No,
don't. Sorry.
it's fine. It's fine. So this is going to be sine of x over cosine of x.
Okay.
All right. Do you see like
You where is it going? Yeah, I see it.
yeah?
Yeah.
Okay.
And
Uh,
you.
this is a pretty famous. Yeah, it's a pretty famous property, which I think you should take care like you should take good time to learn. Sine over
Yeah.
cosine is just tangent, right? That's a big one. Trig identities. I'll show you how to memorize all of them just by writing down a basic formula.
Okay.
Yeah. So we'll get to that later. So sine of
Yeah.
x over cosine of x. All right. Uh, Notice one of them is the derivative of the other,
Yeah.
but which one should we choose for you?
Sine because it's not negative when you get the derivative.
You like it because it's not negative.
Yeah,
All
and
right.
you can just cancel it out.
All right. Well, watch what happens. So u is equal to sine x, and then du is equal to
Cosine.
cosine of x. All right. And so what would our new integral be? I mean, cosine x dx.
Uh, U over 1 times du.
Well, wait, over 1? I thought cosine was du. So we're actually dividing by du. We're actually dividing by du and then times dx over dx. Hmm.
Uh,
Or sorry, it's actually if we rewrite this, it's gonna be du over dx, so du over dx, and then times dx. Hmm.
dang. Okay,
Yeah,
that's not right.
du in the denominator is not great. So
Okay. Oops. Yeah, okay.
yeah, so this is we can't really do much with this. So you
So
should
you would
always
be cosine.
yeah, you should always
Okay.
refrain putting du or like the yeah du in the denominator.
Okay.
So anyways, yeah, so u should be cosine of x, and then du is equal to
Negative sine x.
negative sine of x. Yeah. So uh, dx. So what does our new integral look like?
Sine over u times the
Well,
well,
sine
yeah.
x dx. That's just our du.
Okay.
So du is in the numerator,
Mm.
and then cosine x. That's just our u. So u's
So
in the
it's just the
denominator.
bottom.
Yeah, and this you can compute, right? If you want, we can
Yeah.
rewrite it as 1 over u du. All right.
Yes.
Yeah. So from this one, you learn two things: property of tangent,
Uh-huh.
and you also want to keep du out of the denominator, right?
Okay.
Because from before, you already know that, hey, we found something and its derivative inside the integral, so we could do a basic u substitution.
Mm-hmm.
So now, this is a good property to learn. What is 1 over u? What is the integral of 1 over u?
Ln x.
Yeah,
Or
yeah,
ln u, ln u.
ln u, right? Are we done though? Or this should be negative, by the way. Yeah. Are we done though?
No, you have to sub in u.
Yeah. And
Yeah.
so this should be negative. So this was negative natural log of what did we choose for u?
Cosine.
Cosine. So negative natural log, and we want to see the absolute value of cosine.
Yeah.
Yeah. Because cosine can be positive and negative, right? Let's just keep it at the absolute value. And we're actually
Okay.
good. There's another funny step you can do here where you could say this is equal to the natural log of secant x. Although, from I think this question was also in your review, and your professor actually didn't do this, so I say maybe avoid this one.
Yeah, where in
Like
the review is that one? Like you
uh,
did this question was in it?
I think like this was in your review because I don't
Oh.
like yeah,
Oh, okay, okay.
or maybe it was
Yeah.
like somewhere else, but maybe it was in the notes. But I also did this
Hmm.
question with one of my other students. But
Oh,
anyways,
okay.
so do you know how we got from here to here? Like natural
Uh,
log.
yeah, it's like 1 over cosine, right? Is equal to
Yeah,
secant. Yeah.
yeah. So the negative comes over here, right?
Mm-hmm.
It's a property of logarithms.
Yeah. Oh, okay.
Yeah. Actually, do you know your properties of logs by any chance?
N- No.
No. Okay. Those are important. So in
Okay.
fact, yeah.
Let me
In
see what are
fact,
they? Let's see them.
so and then we'll also do log. Hmm. View and log. Yeah. All right. So back to this. So we'll come to log properties a bit later.
Okay. Bucks.
Let's do one more. This time I think you might be able to do this. So the integral of x to the fifth times sine of x to the sixth dx. All right. Well, what's your first step here?
Find the u.
All right. What's your u?
Make it sine of x because you can make it sine
Well,
or
here's the thing.
cosine x or something like that.
Here's the thing. If we just make like u sine of x, like we're kind of just ignoring what's on the inside, right? We're gonna have to write like sine of x in terms of like whatever u is. So
Okay.
like that way we can turn it into sine x to the sixth. Do you see anything else where its own derivative exists somewhere?
Mm, no, I don't.
All
No,
right.
I don't.
Well, let's look at x to the sixth and
Oh,
x. Yeah,
can you just like make that u x 6?
yeah. You can make u x to the sixth.
Uh,
Du is equal to
uh, 6x to the fifth.
times dx. Yeah. So we have an x to the fifth. We have a dx. Where's the six coming from?
Because that was the power rule,
Yeah.
right?
So
Yeah.
how can we resolve this if there's no six in the integral?
Just put it in front.
Yeah. Yeah, exactly. So we can multiply both sides by 1 over 6.
Yeah.
Right? 1 over 6 du is equal to x to the fifth dx. All right. Is that what you meant?
Yeah. Uh-huh.
Okay. Cool. So we have our x to the fifth and dx. That's going to be our 1/6 du. So I'll write 1/6 out in front. And then, of course, u is just x to the sixth. So we have sine of u du. All right, and you know how to evaluate this.
Yeah, I just put in u, or actually find the derivative, which would be
Well, not the
uh,
derivative. This is the
or
antiderivative.
antiderivative, yeah, sorry, which
Yeah.
would be text, so it'd be negative cosine.
Yeah, the
Is it
derivative.
anti?
Yeah,
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 yeah, negative cosine and sub in u, which is x6, and then that's the answer.
yeah. X to the sixth, and then I'll multiply this by 1/6, and then
Mm-hmm.
plus c. I should add
Plus
plus
c.
c earlier. Yeah. Look, even I'm forgetting it.
Yeah, yeah, everyone forgets plus c.
In fact, do you want me to give you an integral where we know plus c is actually really important? Like, because I don't think your teacher ever like or any teachers, they really emphasize that, like, plus C is really important.
Sure. Yeah, we can look at one.
All right. Actually, before we do that, let's go over the Pythagorean trig identities.
Okay.
Right?
Yeah,
Yeah.
that works.
So, and then like the way you can check if it's negative cosine, right? Take the derivative of negative cosine should get you sine.
Okay.
Anyways, yeah. So, okay. There is equal to r squared. All right. So
Yeah.
you know what this is? It's the unit circle.
Yeah.
Yeah. So this is
Yes.
y. This is x. All right. What I'm gonna do? I'm gonna copy this 3 times. Whoops. All right. So this is all you have to remember, right? You can remember this one easy, right? X squared plus y squared is equal to r squared.
Yeah.
All right. So first, we're gonna divide everything by r squared. And I suggest like using some scratch paper, like at the beginning of the test, and like just writing this down.
Okay.
Right. Then we're gonna divide everything by y squared. And then everything by x squared. All right. Remember what x over r is?
Right? Yeah.
So x is adjacent over hypotenuse.
That's cosine.
Cosine.
Yeah.
Yeah, and this is cosine squared x because these are squared terms.
Okay.
All right. Next, here's our y. In fact, let me just get rid of this one, and I'll just draw the triangle.
Okay.
Yeah. So this is our angle. And this is going to be our r. We'll say r is equal to 1. Right? This is our y, this is our x. Now, if this is 1, like our y is going to be, our y is always sine,
Okay.
and our x is always cosine.
Okay.
So in other words, yeah, cosine divided by 1, that's just cosine. Alright? Sine divided by 1, that's
Just sine.
sine. And then 1 divided by 1.
Just 1.
Alright, cool. So look, that's your first identity.
Okay, so cosine.
This is a big one.
It's a big one. All right, let me write it down.
So, do you see the strategy here?
Yeah.
You're taking your original Pythagorean identity, right? And you're just dividing by each term, and that'll just get you 3 different identities: x, y, and r.
Okay.
So, what is x over y? So cosine over sine.
Tan. Wait. Cosine over tan. That's not tan.
Cosine over
Cosine
sine.
over. Yeah.
It's not
Inverse
tangent.
tan. Inverse.
It's cotangent.
Cotangent. Yeah. Okay.
Yeah. Inverse tangent means the opposite of tangent, right?
Oh yeah.
So
Okay.
like in other words, whatever number you would plug into tangent to get something out, you plug in the output to get whatever you plug in. That's inverse tangent. That's an inverse trig function. Those are ugly, so don't even bother.
Yeah, I don't want to deal with all those.
Yeah.
Screw all.
So cotangent x, your cotangent squared x, y divided by y, that's sine over sine, which is
1.
And then finally hypotenuse over sine. So in other words, 1 over sine.
That's secant.
Close. It's
Squared?
cosecant. Yeah.
Oh, cosecant.
Cosecant squared. All right. And then finally, x over x. That's just cosine over
1.
cosine, which is 1.
Yeah.
Right. Y over x. That's sine over cosine.
Sine over 1. Just wait. Oh yeah, sorry. Sine over. That's tan. That's tangent.
That's tangent x, right?
Yeah.
Tangent squared x. And then finally, 1 over cosine.
That's secant.
That's secant.
Okay.
Whoop.
Oh.
Yeah. I clicked the little end there. All right. Yeah. So the ones on the end here are actually the really big ones. So those are the ones you should like. If you're not gonna memorize like the whole strategy of getting there, then you should at least just memorize these two because
Just the identities? Okay.
yeah. But if you
Sorry.
forget the identities, then you could. This is an easy way to generate them, right?
Yeah.
Yeah. Do the Pythagorean stuff and then divide by each term. All right.
Okay.
Now I'm gonna use one that uses or that puts some emphasis on plus c.
Okay.
So the integral of sine x times cosine of x dx. So there's actually two ways to do this. So just pick what do you think your u should be? Pick a u.
Sine.
So u is equal to sine of x, and then du is equal to
Cosine of x.
cosine x dx. So what is our new integral going to look like?
It's going to be the integral of u times du, no?
Yep. And then do you know how to evaluate this?
Yeah, just you'd be u squared over 2. And then you sub in u, which is sine. So sine squared over 2.
Yeah. Sine squared x over 2. And then, of course, plus c.
Plus c.
And then let's do the other one. So in which case, our u is going to be cosine of x. So what's du?
Negative sine.
All right. So what does our integral look like?
Du times u? Or negative du.
Yeah,
Negative
so we could say this is negative u du,
Yeah.
right? Because it's all multiplied. It doesn't matter the order, right?
Yeah.
That's the cool thing about real numbers. So anyways, after that, can you evaluate the integral?
Negative u squared over 2.
Yep.
And then sub in u, which would be cosine x. So negative cosine x, yeah.
Yeah, negative cosine squared x over 2 plus c. Notice, from the same integral, we got two different answers.
Yeah.
But notice, sine of x does not equal cosine of x. Right? If I plug in 0 for sine x, that's not the same thing.
Yeah.
So what's going on here?
I'm not sure what's going on. It's a weird graph.
The c's are different.
Ah.
So in other words, for whatever value of c we choose, we'll actually get different answers, right? If you check over here, sine squared x is cosine squared x is equal to sine squared x plus 1. We could say that sine squared x is equal to 1 minus cosine squared x. Wouldn't you agree?
I would agree.
Yeah. So in which case, if we rewrite this, 1 minus... So if we write this as 1 minus cosine of squared x over 2 plus c, right? Notice, we could also take out the 1/2, so this is equal to 1/2 minus cosine squared x over 2 plus c. So this is why they were different, is because this c was slightly smaller than this c, because it contained that half.
Oh.
Which is why you always... This is why you always have to include plus c, because you don't know if like you're adding or subtracting something. Right?
Okay, so okay, I get it. That's cool. I did not know that. Okay.
Yeah, which is why plus c is really important. Look at all the math we did so far.
Yeah, Jesus, my goodness. Yeah, it's been like an hour. Alright.
It's actually been 29 minutes.
Oh, dang.
Yeah, just into the recording.
Okay. Got time now.
Yeah. So let's see. So we did that one, and then I said that we were going to do. Okay. Trig sub. That one is
the devil.
Yeah.
I know one identity where it's x squared. The plus one is tangent, which is a times tangent x, and then you get the antiderivative of that, right?
Did they also? Did you also go over like choosing a let's like? Did they make you like after you're done like doing some integral you had to like draw the triangle
Yeah, they
because
made you do that. Yeah,
okay
that's how you actually called it. Yeah.
okay just making sure so
Yeah.
let's just choose one of the more basic examples so the integral
Okay.
of 1 over the square root of 1 minus x squared dx.
Okay.
Yeah. So I'm actually going to do this one for you.
Yeah.
Because
I'll
I,
follow
I,
along.
I want to give you a taste of like what you should be looking out for.
Okay.
So I see 1 minus something squared, and if we go back to our trig identities, notice sine and cosine are actually derivatives of each other, and they also show up in this one. So sine and cosine are actually ones that you should choose pretty often if you have a square root in the denominator, sine or cosine, right?
Wait, so do you use trig sub when you have any kind of trig function in derivative, or only when it's only in denominator?
I'm not sure I'm following. What are you asking?
When do you pull out trig sub? Like when it's 1 over square root of something? Is that when you use it?
1 over square root of something, or just 1 over. Okay. So in other words, you're gonna have 1 divided by, and then it's gonna be something.
Yeah.
But you're gonna have an x squared in there somewhere, right?
Oh. Uh-huh.
Because in which case, when you do the trig sub, right? Like let's say there's like a square root inside. That square root will simplify, and then you'll have a regular trig function. In which case, that and that would just cancel out, and you'd be left with like a u or something.
Okay,
So,
yeah, I remember that, yeah.
I'll like I said, I'll walk you through this one.
Yeah.
So, I remember that. Let's go back up here. Yeah, sine squared x is 1 minus cosine squared x. So, sine squared x is equal to 1 minus cosine squared x. So notice this kind of looks like this. So in other words, if I replace x with like cosine of theta, right? Let's see where that takes us. So x is equal to cosine of theta, so what should dx be? Oh, in this case, by the way, we're not replacing a portion of our function with u. Instead, we're replacing a small thing with something else. In which case, we could just get rid of x and dx on their own. Okay. The good thing about trig sub is that it doesn't get as messy. Like you'll do a lot of canceling later on.
Yeah.
Anyways, sorry for interrupting. So what is our dx here?
Negative cosine.
Not negative cosine.
Oh, just regular cosine?
No, our cosine is we're taking the derivative of cosine.
Oh, sine.
Yeah,
Oops,
negative sine. Yep, there you go. Right, and so our new integral is going to look like, well, dx is negative sine of x, or actually sine of x, sine of theta, d theta.
Yeah.
So we can say put negative sine of theta up here, and then d theta over here. So negative sine theta over here, d theta over here. And then we have the square root. What would be in our square root, by the way? Can you tell?
1 minus cosine squared.
1 minus cosine squared x. Where have I seen that before?
Up top, right there. Oh, which is equal to sine x. I'm sorry. Yeah, okay.
Yeah, negative sine of theta. I have to remember to put everything inside of theta.
Yeah.
So 1 minus, or this is actually divided by the square root of sine squared theta, d theta. Look at that. Sine of theta is squared and has a square root. So it just cancels out.
It cancels out, yeah.
Yeah. The only ugly part is actually just subbing everything in, but like after that, everything just cancels. So we have negative sine of theta divided by sine of theta d theta. All right, what's that equal to?
Negative on the outside, right?
Yeah. We can move the negative on the outside,
And then just 1.
Yep, that's just 1, and so we could just say that's d theta.
Oh shit.
All right. Do you want to evaluate the integral now?
D theta is equal to. We don't have a d theta, do we?
Well, just think of this as 1.
Oh, just think of that. Oh, then it. What? Oh, is u squared over then? Like you do the u squared version?
Well, think of this like the derivative of what gets you 1.
Derivative of x.
Yeah, but instead of x, we're writing it in terms of theta. So what should our answer be?
Theta.
Theta. All right. Are we done?
No.
We have to write things in terms of x. So
yeah.
X is equal to cosine of theta. So this is when you're going to use the anti-cosine, right? So in other words, x is equal to arc cosine of theta. Or sorry, arc cosine of x is equal to theta. All right. Yeah. And so that means your answer is arc cosine of x. By the way, maybe your teacher she probably used like cosine like inverse of
x.
Same
thing.
No, I hate this though because like this is not the same thing as like it looks like 1 over cosine of x.
Mm-hmm.
It's not the same thing,
not.
which I hate so much. So you should just like use arc cosine instead.
Okay.
This is a much better. Yeah, it's a much better format.
Okay.
All right.
Yeah.
So let me actually see if I did this right. So, substituting cosine, negative sine squared. Yeah. So that just gets this d theta.
I'm copying all that down. Sine, theta. And then those cancel out, which leaves you negative integral sine.
And of course, plus c. I should probably.
Oh, yeah.
Negative arc
theta. And then arc cosine.
Yeah. I forgot to put in the negative again. So.
And then plus c. So it's negative arc cosine plus c.
Yeah, negative arc cosine x plus c. Yeah, you got that. Also, if we wrote like our x is equal to sine, then we could also say that this is arc the sine of x plus c. This time we can actually we can actually bar the negative because the derivative is not negative. It's just negative cosine.
Okay. I'm starting to get it, yeah.
So either one works.
Okay.
Alright. Let's do. Okay. Now I'm going to throw in some constants.
Okay.
So let's do this.
Oh yeah, this is where you got to do the x part, right? Or like the x over something, and like make the triangle.
Yeah, I think so. So
okay,
I'm gonna do the integral of dx, or 1 over the square root of 4x squared plus 9 dx. So with these constants, so we want to get something that like something squared plus 1, right? Get out of these. Do you see like something squared plus 1 or 1 plus something squared?
Yeah. Yeah, you can make the 9 a 3, right? Oh wait, yeah, yeah, right there,
You could either do a cotangent or you could do a tangent. Notice
yeah.
the derivative of cotangent is like, honestly, I don't even know. It's like,
Huh.
yeah. The derivative of tangent, let me just double check. Yeah, the derivative of tangent is secant squared. And notice, there's a secant up here. So, yeah, we're actually, you're more inclined to use this. So, like, the two that I circled, like, those are the bigger ones.
The bigger ones, yeah.
Yeah, or, like, the more important ones. You're going to use those more often.
Okay.
So, we're going to have x is equal to, well, according to this, it should be tangent. But, so actually, let's factor this out. So it is 1 over the square root of 2x squared plus 3 squared.
Yeah.
All right. So we want this to eventually be 3 tangent squared x plus 3 squared, because that'll eventually equal 3 squared. So this is going to be equal to 3 squared times tangent squared x plus 3 or plus 1. Right. So our end goal is to try to get this in our denominator.
Okay.
So, but let's see how that goes.
Yeah.
So our theta should be equal, or actually, sorry, 2x. So 2x, because we're trying to do this fancy stuff, is equal to 3 times tangent.
3 times tangent. Okay.
All right. 3 times tangent theta, d theta, or no, not d theta again. So, can we take the derivative of both sides?
Of that one, the 2x equals 3 tan?
Yeah.
Yeah, I think we can.
All right. So, can you take the derivative?
Yeah, it would be 2
2
equals,
dx.
2 dx equals, it's a constant, so and then sine over cosine? Or no, secant squared.
Yeah, this is secant squared.
Theta.
So this is 3 secant squared theta. All right. And of course, we don't have a 2 over here, so we could just, like, multiply both sides by 1/2. So dx is equal to 3 over 2 secant squared theta. Do you know how I got here?
2x equals 3. Oh, yeah, you have to substitute the x.
Yeah.
Because
So
that's your thing, yeah.
So
Okay.
I wanted to get rid of this constant.
Yeah.
And I wanted this 3 to match up with this 3. That way, after we square it, we have 3 squared and 3 squared, and the 3 squared just factors out here. And we know what to do with this. It's just secant squared.
Yeah.
So that's why I chose that. Maybe I should have like only added one constant, but your strategy is to, like, whatever constant here is going to be 2. Right?
Yeah.
Do you know how I got 2
I think our teacher, like, gave us formulas where it was like a equals something x, like, dependent on that, like, depending on what's in the square root, like if it's x squared plus a, it's the tan one, and then if it's like a squared minus x squared, it's like secant tan. It's something like that.
Yeah.
Right.
So
Yeah.
it's, yeah. There there should be like a ton of formula sheets online, but
Yeah.
honestly, just don't even bother with the formula sheets. Like, if you're just like, if you can get pretty clever with like how you do the substitution, like, honestly, a lot of like the smartest math people I know, like they don't even care about formula sheets.
Yeah.
They think it's better that you learn like the concept with it. So,
Yeah.
the way you got 2 and 3 is because, like, this is 2 squared, this is
that's
3
3 squared, yeah.
Yeah.
So they have to be square roots, right? In the
They have to
bottom
be squared because you want to get rid of the square root. That's your whole goal. All right.
Yeah.
So let's rewrite our integral.
Okay. So it would be
So d theta. So 2x is equal to 3 tangent theta. So we get the square root of 3 tan theta squared plus 3 squared. And then dx is equal to all of this jazz. So I'm actually going to move the 3/2 out here. And we'll put the secant squared theta d theta.
Secant squared theta d theta. Okay.
Yeah.
And then you can get rid of the sign bottom, or you can get rid of the square root at the bottom, right?
Not yet. You have to factor out the 3 squared.
So
Yeah. Because we have an addition here, right?
Mm-hmm.
Yeah. And so, like, sum of squares is not the sum, like, the square root of the squared sums is not the sum.
Okay.
I don't know. Yeah. So we have 3 squared, 3 squared times tangent squared theta over secant squared theta plus 1. Alright, d theta. Alright. So, do you have any questions so far? Any confusion about how we got from here to here?
I think I'm good.
Yeah. So, I saw that there was a 3 squared here and a 3 squared here. So I
you just
factored
factor that,
yeah, and so we have tangent plus 1.
Yeah. So your end goal is to get that identity, like tangent plus 1 or secant
Yeah.
plus 1 or something
Because
plus 1.
after that, everything is in terms of squares, and so the square root is just gone. Alright, so 3/2 times the integral of secant squared theta over 3 squared times secant squared theta, and that's all in the square root d theta. You know how we got from here to here?
Yeah, tan squared plus 1 is equal to secant squared.
Perfect.
Yeah.
Alright. Do you know what we can do from here now?
Get rid of the square.
Yeah, and so what are we left with on the denominator?
3 times secant.
Yeah.
To the
3
theta.
Secant theta, d theta. Notice this secant and that secant, they cancel out. This 3 and that they cancel out. So you're just left with
1/2.
1/2 times secant of theta d theta.
Okay.
So this is kind of my fault because like secant theta is unfortunately one you're just gonna have to memorize.
Yeah, that's fine. I
Yeah.
kind of knew that with math. You just gotta memorize everything.
Yeah. You unfortunately, I hate memorization. Right. I'm actually never really good at it. But the integral of secant theta, we'll have the 1/2 here. That is the natural log of secant x plus tangent x. Alright?
Okay.
Yeah. Alright. Are we done here?
Oh,
Alright, sorry, this is secant theta, tangent theta. Are we done here?
no.
No, we still gotta put in stuff for theta.
Yeah.
Alright. So let's see. Theta okay. 2x is equal to 3 tangent theta. So let's write that again. So 2x is equal to 3 tangent of theta. Alright. I'm actually gonna let's actually move this over here. So 2x is equal to 3 tangent of theta. So let's divide both sides by 3. So In other words, we have tangent of theta is equal to 2x over 3. So far, so good? We want to get the trig identity by itself here to draw the triangle, alright?
Mm-hmm.
Alright. Now, what is tangent? Tangent is what over what?
Well, I got it written down. Hold up. Opposite over adjacent.
Opposite over adjacent. So that means it's 2x over 3.
Yeah. And then that missing angle is your OG thing, the square root of 4x plus 9.
Yeah. Look at that.
Nice.
Yeah, and this is Pythagorean identity, right?
Uh-huh.
Yeah. 4x squared plus 9, right? Yeah. All right. So we wanna evaluate. Whoa. MS Paint is lagging.
No, you're good. You're good.
That's a first. So
Too much knowledge.
ln. Yeah. So natural log. So secant of theta. Do you remember what secant is?
Secant, like what do you mean?
So our answer was secant theta.
Oh, you
Yeah.
mean like the
Yeah. So look, we have those identities. Now we just have to look at a triangle and see what we get.
Yeah. So
secant what's
was,
secant? Yeah. Secant is what
It's-
over what?
it's the opposite of sine, so it would be
No, it's the opposite of cosine.
opposite of cosine. So
Yeah.
it would be
The cos are
hypotenuse over adjacent. Hypotenuse over adjacent.
yeah. So
Okay.
so in other words, it's this over this.
Mm-hmm.
Yeah. So in other words, it's
Let me just put that in.
all right. And then finally, we have our tangent.
Yes. Tangent is equal to adjacent over hypotenuse. No, wait, I lied. Opposite over adjacent.
Yeah, opposite over adjacent. And notice, like we already have tangent over here.
Oh yeah, 2x
Yeah.
plus 3.
Yeah. So 2
Or 2x over 3.
All right. Look at that.
And that's it. Oh my goodness.
We
Wow.
had a whole page full. So in other words, the integral of all of this will get you this.
Wow.
Don't sue me if I made a mistake somewhere.
It looks good. It looks like what we learned. It seems easier than what we learned, the way you taught it. So that's helpful.
Thank you.
For sure. Wonderful.
Yeah. So your strategy, just get rid of the square root and then integrate
Mhm.
normally.
Okay, that's not that. Yeah, it's just hard. It's like so much memorization and knowing identities and all that stuff. That's what
Yeah.
gets me. Like the
That's right.
process itself doesn't seem that hard. It's just normal use of and everything, canceling out, factoring. But that stuff is like, yeah, rough.
Yeah. And in fact, the reason trig sub is so necessary is because, like here, like a squared plus x squared. You can't simplify this, right?
No.
No.
Oh
But-
wait.
No,
You said you can or you can't?
You can't simplify it.
Oh yeah.
Right? Yeah. So, but with trig sub, this allows you to simplify it, right? Because what we did here, we factored out like a common term, and then we turned like the sum of addition into just one square, right? Which is just sine squared. And then that allowed us to take the square root. That's why trig sub is so necessary. Is because it turns something that we can't simplify into something we can.
Okay. Yeah, I get it a lot more now. Okay. That's definitely. There's probably only going to be like one trig sub question on my test. So as long as I can get the one, I think I'll be good.
Yeah.
I'll
So
be
in other
chill. I
words,
think.
just something in this term, like if there's an
Yeah.
addition, trig sub is gonna happen.
Yeah, the way she taught us, like the identities was like 1 over, and then because it's a squared plus x squared, it's the only one with the plus in it, that equals tan, and then the other one's like x squared minus a squared, that one equals, I forgot, there's notes on it, I can look it up and just memorize those. But she like gave us identities for it, to make it a lot easier.
If your professor like here's the thing, I don't think professors should teach to memorize. Like if you want to memorize something, like you'd be better off just looking up like how to do it and then like asking Google to give you the answer, or like using Google to memorize.
Yeah, that's pretty much what I've been doing.
Yeah. you know, what once you get into like graduate courses, they like you're not asked to memorize as it is to show like how things work.
Yeah,
Right?
I don't think I'll ever get to graduate level though. I'm good on that. I'm good with my 7B knowledge, and I'm good on that. That's all I need to know about math, trigonometry, and integrals as far as it goes for me.
All
I'll
right.
be chill.
All right.
Um, I think that's low key it though. I think I got everything.
Well, okay. So we did U sub, we did trig sub, and
Yeah,
then do you want to just review integral like basic integrals and then properties of logs?
yeah, that works. Like basic
Okay.
integrals. Yeah. Oh, maybe we
Uh,
can do a integration by parts. One of those questions.
oh, did they? Okay. So did they teach you that the integral of u dv
Times
is
du is equal to u times v times the derivative of u times v.
so v du? Did they teach you? They taught you this?
Yeah, yeah, yeah.
Really?
I'm looking at it right here.
Wow. Okay. Because like this is like what an introductory calculus course.
Uh,
Is this your first
no, it's
calculus?
second. It's the second one.
Second.
I had my yeah. This is B, so I had A over summer.
Okay. Oh, okay. And
Mm.
then, did they also teach you about like infinite series?
It sounds a little familiar, but it's not on our test or nothing. She probably like mentioned it.
Like
It's like a little. Oh, by the way, this exists.
yeah. Okay. So like the derivative of like 1/n to the r as like from r equals 0 to r equals infinity is just equal to 1 over what r. It's equal to, like, have you heard of that? Like the geometric series?
No, I don't think she mentioned
No.
it.
Okay. Then don't worry
Yeah.
about that. Yeah. That's
Okay.
probably. Is there like a 7C class that you have to take?
Yeah, there is, but I don't have to take it. My
Uh,
last one is 7B.
okay. Yeah. Because that geometric series you'll probably find that seven class.
Oh yeah,
Okay.
I'm good on that. I'm
Yeah.
chill.
So, anyways.
Oh yeah, I know the formula though.
Yeah. Do you know how we get this formula?
It's like the reverse of the not the power rule. What's like? Oh, I don't know the name of it. It's like the reverse of one of the
The
derivative
product
one.
rule, right?
Yeah,
Yeah.
product.
Yeah. So like u of x times v of x, right? This is
Yeah.
right. The derivative of those two is equal to u
D.
times dv plus d or u times dv plus v times du, right? You take the
Yeah.
integral of both sides. So the fundamental theorem of calculus says that the integral and derivatives they cancel out,
Mhm.
right? And so uv is equal to the derivative of u dv plus the integral of v times du. And then of course you subtract this one from the other side. So the integral of u times dv is equal to uv minus the integral of v minus du, or
Oh
v times
wow.
du.
I never saw how they go from that to that. That's pretty cool though.
Yeah. So you
Huh.
just take the integral of each one, and then you subtract this one over.
Okay.
Yeah. And you subtract it over because it's easier to turn one integral into something else in one integral instead of adding a second integral and then turning it into that.
Yeah, I'd imagine it's definitely a lot
Yeah.
easier. Uh-huh.
All right.
You want me to like pull up? Or yeah, sorry, you go.
So this one should be. Have you done one where like it's you take the derivative over and over and you eventually loop back to itself, and then you have to subtract the original integral minus the last integral, right?
Are you talking like doing it like two steps, or like you taking the integral twice? If it's like an x to the third, you have to like do it twice. Is that what you're
so,
talking about?
so in other words, like if you do something with like e to the x cosine of x, right? This will eventually be like e to the x sine, like then that, and then eventually you'll get like a bunch of jumble stuff, and then e to the x cosine of x, and you know that this x cosine of x is equal. So it's equal to that plus this jumbly bit plus that. So you subtract that from both sides and you solve for this if it's equal to 0. Have you done
Yeah,
that?
I don't think I've ever
No?
seen that.
Okay.
No.
Yeah.
Yeah. I think you're just like basic integration by parts,
Okay.
where it's just the UV, DUV stuff like that.
Yeah. Okay. So in which case, let's just do a really basic one. So we have
Yeah.
x times cosine of x, right? Dx. So whatever you choose your u to be, you always want that to like sort of decrease. So in other words, you can't take the integral of that forever. A trig
Yeah.
function, right? An e to the x, a 2 to the x. A trig function is like
V prime is the one that's in there in U. It's V prime
yeah,
times U, right? Okay,
yeah.
yeah.
So in other words, you do not want these to be u. You want this to be dv, right?
Okay. Yeah.
Because those you can integrate forever, but you have to stop right at some point. Otherwise, like
Mm-hmm.
So anyways, yeah. So this should be your dv, and this should be your u, right?
Yeah.
And so normally people would write, okay, u is equal to x, and then dv. So u is equal to x, then dv is equal to cosine of x,
Yeah.
and then du is equal to
1.
1, and then v is equal to
Negative sign?
uh
This sign.
no, it's just sine. Right?
Okay, this sign.
The derivative of sine is cosine. Right?
Okay.
If you just because when
Oh,
you,
yeah. Mhm.
I think now you're in calculus, like you should know that like between derivatives and integrals, like integrals are like the bigger monster. Right?
Yeah.
Yeah, I think you got it to the point where you memorize that. So
Mhm.
instead of just like questioning like if the integral of something is something else, just take the derivative and see if it matches up.
Okay. Okay.
All right. So in which case, this is equal to, well, we have ud minus v du. So what's our uv?
X times sine X.
All right, and then minus what's your v du?
1 times cosine X, which you just integrate cosine.
Well, no, v du. This is v. This is u. So v du. So it's just sine.
Oh,
of x.
sorry. Yeah. Sine of X.
All right. And then you know how to take the integral of this, right?
Yeah, it's just cosine.
Well, is the derivative?
Oh, negative cosine.
Negative
cosine.
Yeah,
Yeah,
but since we're-
and then plus, so yeah, it'd be
Yeah.
with E plus.
yeah, cosine of x and then plus c, right?
Yeah. C.
There
These
is.
ones aren't too bad.
Yeah. There is. I would like to say a better way, or like, you. It's essentially writing out this, but
Uh-huh.
yeah. By the way, you know how like every time you take this integral, right? It becomes negative.
Yeah.
If like let's say you added on another integral, like, or like let's say like this was x squared and this was just x, right?
Mhm.
Right. Notice this integral would become positive, right? And then if you add
Yeah.
another integral, it would become negative and then positive, right, etc.,
So
etc.
it just alternates, yeah.
Yeah, so plus minus. And so there's this thing called the DI method. So in other words, let's do x to the 5th cosine x. Or no, not x.
Ooh.
Let's do x cubed cosine x.
Yeah, it's a little, yeah.
Yeah. All right. So DI, in other words, it's finding what you take the derivative and what you integrate, right?
Uh-huh.
Sort of like here, we want to take the derivative of this and integrate this.
Yeah. I think I've seen this on TikTok. Maybe. Like, it looks kind of familiar.
When did I see this? God, it was forever ago. Maybe I saw this before TikTok, but
Jesus, prehistoric times.
oh my god, yeah, tell me about it. So, what do you think we should take the derivative of? Just by looking at this, what do you think always decreases or like eventually goes to 0 when we take the derivative of?
X3.
Yeah, x cubed, and then the integral is cosine x. You always want the whole, like you don't want to just leave stuff out. You can't just make up rules. All right.
Okay. Mhm.
Now take the derivative of x cubed.
2x to, or 3x to this one.
Yeah. Yeah, 3x cubed,
X,
and then the next one is,
6x.
and then the next one is,
6.
and then finally,
0.
yeah. You always want to go to 0.
Okay.
Right. Then, what's the integral of cosine x?
Sine x.
Sine x. Integral of sine?
Negative cosine.
integral of negative cosine.
Negative x. Or negative sine x.
Negative sine of x. And then finally, the last one.
Cosine x.
Yeah. Notice it always goes cosine, sine, cosine, right? And then it goes positive, positive, negative, negative, positive. Yeah.
Okay.
All right. Now, what we're going to do, we're going to go backwards, right? Because we have our v, so we have our uv, and then v du, and then u and v, and then u and v, etc., etc. So it's going to go diagonal like that. So we're going to
I've seen this on TikTok, yeah.
Yeah, we're going to multiply diagonally. But notice, remember how every time we integrated, it always became negative?
Yeah.
Yeah, so it's going to be plus, minus, plus, minus, plus. All right?
Uh-huh.
Let me just double check something. You
Can you do this for derivatives that, like, let's say it was x cubed or x squared? Could you just do it? Could you do this too?
Yeah, you could even just do it with x. Like,
Okay.
Yeah. Yeah. So, yeah, you start with positive. Like, if you just did it with x, then, like, you would only... Whoops. This is called the tabular method, by the way. I just call it the DI method. But, like... Yeah. Because you're using a table. But, like, if it's just, like, x, then you'd just be using the first two columns.
Yeah.
All right.
Yeah, because you'd stop at zeros.
I guess the first three columns? Yeah, because you'd have these two. Yeah. So you'd stop at 0.
Oh, so wait, then, so the derivative would be x3 times sine x, and then minus 3x minus cosine x, and then plus, is it like that, and then plus 6x?
So, yeah, so it's going to be negative 3x squared minus cosine x, and negative times negative is positive.
It's times.
You
Okay.
multiply. So 3x squared times cosine x, and then 6x times negative sine of x is negative 6x sine x, and then we have negative 6 and times cosine x, so negative 6 cosine of x. Look at that.
Dang, okay.
Plus c.
I get it. That makes everything so. That basically, that's like an easy ass way to do them. That's awesome.
Imagine doing this like the previous way.
Yeah.
It takes forever, right? You know, you'd have to find u and v at the same time.
du at like 3 times, yeah.
Yeah.
Okay. Awesome.
And then, just in case, I'm going to show you, like, a very niche situation.
Okay.
So, in other words, let's say we're going to do the integral of e to the x sine of x. All right? This one you might not know, but, like, just in case, I think this would help. So
wait, don't they both just keep going? Like neither of them can hit 0?
Exactly.
Yeah.
Right? So di, right? So what's the derivative of, like, or pick something to take the derivative, pick something to take the integral.
I guess. And there's like a
It actually doesn't really matter.
It's ex.
All right, so d is e to the x.
Yeah.
Or okay, e to the x, and then I is sine of x. All right, integral of sine of x.
Negative cosine of x.
Negative cosine of x.
Or negative
integral
sine
of
of x. Negative sine of x.
And
then cosine of x, and then sine of x. And you flip it, so it's negative cosine of x. And you just keep going.
You see, it repeats, right?
Yeah, it repeats.
What about e to the x?
E to the x.
E to the x.
E to the x. E to the x. E to the x. All the way down.
All right. Let's do plus, minus, etc. So we have that. But when we stop, we actually look at just a random row, right? So
yeah.
If you notice, this row, right? This row up here is actually the same as the bottom row.
Yeah.
Right? All right. So let's write this out. So the integral of e to the x sine of x dx is equal to e to the x, or negative e to the x cosine of x, and then plus e to the x, or plus, yeah, e to the x sine of x, plus e to the x cosine of x, and then plus, minus e to the x sine of x, and then finally we look at this row, right, like the row down here, and that's plus this integral e to the x sine of x. So notice we can actually just subtract the integral from both sides. And we just have,
that's what you're talking to me. Yeah.
yeah,
And then just,
e to the x cosine of x plus e to the x sine of x is equal to 0.
Okay.
Yeah. And then, of course, like, let's say you have, like, e squared x in here, right? This would be, like e to the, like, this was, like, e squared x, right? Then you would have 2, and then 2, 4, 8, 16, right? And so you'd have 16 times the integral, right? You would subtract 16, or you would subtract 16 from both sides, right? And so you'd get negative 15 times the original integral, right? And then divide everything by negative 15, and so your integral is equal to all of that jazz divided by negative 15.
Okay.
So
dang, that's a lot. My goodness.
Yeah. Just imagine doing this by like the other way we just did, right? The UDV.
Yeah, that's not happening.
This was only one step, right? So.
Dang. Okay. Okay, I get everything a lot more now. This is helpful.
Yep. Yeah. So, when you're doing this sort of integration, just do this one, like.
Yeah. The DI method.
Mm-hmm.
Okay. Cool.
And then these ones are the ones you should be taking integrals of, right?
Okay. Yeah. Alright. I think I got everything now, dude. I think I'm good.
I'm gonna give you one challenge problem, and then
Okay.
I'll let you go. So the integral of natural log of x dx. This one you should actually use integration by parts.
Oh, really?
Yeah. Well, you don't know the integral of log of x.
Oh yeah, true.
Yeah. So let's try to take the derivative.
Well, isn't the integral of? Oh wait, I'm thinking of 1 over x.
You're thinking
of 1 over x.
Yeah. You're thinking of this, right?
Yeah, that's that one. Yeah, that one's easy. Okay, yeah.
But this is a bit harder. So you should probably take the derivative of ln x, and then the integral of 1. All right.
Oh yeah.
So what's the derivative?
What?
Right, because this is 1. This is 1 times ln x.
No, I get that, but wouldn't you make the 1 to the d because that goes to 0 eventually?
Here's the thing: if we're trying to integrate ln x, like we might as well just do the integration right away.
Oh yeah. Okay.
Yeah, we're already trying to take the integral of ln x, so it doesn't really matter. So, what's the derivative of ln x?
1 over x.
1 over x, and the integral of 1.
X.
So we have the integral of, so in other words, this is ln x plus x, and then minus the integral on the bottom, which is 1 over x times x dx. Do you notice something strange about this?
That's just equal to 1.
That's just 1. So ln x plus x, or sorry, yeah. Ln x plus x minus
the integral of 1.
Yeah. Actually, hold up. Did I mess up somewhere? Oh wait, no, it's not. It's not. No, it's x. It's x times ln x.
Okay.
Yeah, you're multiplying. No.
Oh yeah. You're right.
Yeah. So let me just get rid of all of this. Yeah. So it's going to be x times ln x minus whatever the integral is, which is just 1 over x times x dx.
Which equals to 1.
Yeah. So what's the integral of 1?
0. Wait, no, x.
It's x.
Yeah.
plus c. So you see, that's the integral of natural log of x.
Let's see. Got it. That is super useful. Oh my goodness.
All right. Cool. Did you want to go over properties of logs, or are you ready to leave?
I think I'm good on the properties. I don't think we need to know them that bad, but
Alright.
I appreciate the help. Do you think you could like send me this recording so I can study it later tonight too?
I'm actually gonna upload this to YouTube, and then
Oh, okay, cool.
Yeah.
Awesome. So just send me your YouTube channel then, and then I'll watch it.
yeah, of course.
All right.
All right, cool. And I also usually send along the file as well, right?
Yeah, like you're gonna send me the file of the notes you just took.
Yeah, yeah. All right.
Okay, yeah, that'll be awesome. Yeah.
All right. So, you happy with the session so far?
Most definitely, yes. This helped a lot.
All right. Awesome. Cool. Well, good luck on your final exam.
Thank you. I think if I get an F, I'm still gonna pass with the C, but I would not like to pass with the C. I'd like to get a little bit higher.
All right.
So thank you for this.
Yeah. Tell me how you
Alright.
did. All right. Yeah.
I will.
see
I'll
you.
let you know. All right, thank you. Have a good one.
You too.